in this session, we will try to understand the deficiencies of DFT which we have studied in the earlier sessions, and then try to find out another algorithm called as a fast Fourier transform. Let us look at some different varieties of algorithms which are present, which are common, in fact which are easy to use fast Fourier transforms. We will look at them and then try to differentiate between DFT and FFT, and we move on. Okay, let us start with the fast Fourier transforms. Okay, fast Fourier transform, as I have told you, is an algorithm which can efficiently compute the DFT. Before actually we understand the meaning of efficiently computing the DFT, let us first understand or recollect what is the formula for DFT, what are the number of complex computations needed in DFT, whether they are additions or multiplications, and understand how many are needed, and then we will see the importance of reducing these computations, whether they are additions or multiplications. Okay. The DFT of a sequence x of n of length n is expressed by a complex valued sequence. As you are aware, x of k, capital X of k, is what is used in representing the DFT of a sequence x of n. That means, if you can think of, these are the notations which we are all proficient with, and then this is the sequence which I call it as this, we say it as the DFT. The DFT of this x of n. So, what is the formula for this? As you see in the slide, the formula for this is given by summation n is equal to 0 to n minus 1 x of n e to the power of minus j2 pi k n by n, where k lies between 0 and n minus 1. So, let us just recollect this, let us just write down here. So, what essentially this is, it actually consists of two parts, n is equal to 0 to n minus 1, this is the summation, okay, and then the formula is given by x of n, okay, and this is multiplied by complex expression j2 pi n k by n. Okay, so, this is the formula for calculating the DFT. As you are aware, this involves summation and also simultaneous multiplication. So, it is multiplication plus addition that actually gives us an idea how to calculate DFT, where k again varies from 0, 1, 2, okay, up to n minus 1. So, this is how DFT is calculated. The essence of this equation, or the point which we are trying to drive in today in this equation, is it involves not only a summation as is given by the sum of terms, but also a product. Now, we will try to understand how many number of additions we have to do. Also, we have to understand how many number of multiplications we have to do, and remember, these are complex additions and complex multiplications. Now, from this equation we will try to understand the difficulty in calculating DFT, or in other words, how many computations are needed. Invariably, the number of computation we use is dependent on the capital N, that is the sequence of the length of the sequence of x of n, and the complexity increases as n increases. So, we have to understand how best we can remove this complexity in terms of the number of additions and multiplications we are doing. Now, let us define some words. Let Wn be the complex valued phase factor, which is an nth root of the unity and is given by Wn is equal to e to the power of minus j2 pi by n. Now, what I can do is x of k can in fact be written in terms of Wn. As you see here, x of k is equal to summation n is equal to 0 to n minus 1 x of n Wn n to the power of k, where k lies between 0 and n minus 1. So, in effect, what we are trying to do is we are trying to introduce another factor called as w, so that we can rewrite the above equation. Similarly, I can write down the inverse discrete Fourier transform as below. Okay, so how do I write that? As you see here, we are writing this inverse discrete Fourier transform in terms of Wn, which is also called as a Twiddle factor, as we have seen earlier. So, x of n is equal to how much? It is 1 by capital N, a summation k is equal to 0 to n minus 1, x of k W n minus n to the power of k, where n lies between n minus 1 and 0. Okay, so, this is how IDFT is also written as. Now, let us see what is that makes calculation of DFT so cumbersome, or why does it take so many computations are needed in the calculation of DFT. Okay. So, let us see this. For each value of k, The direct computation of x of k involves n complex multiplications and n minus 1 complex additions. As we see here, the summation is from n is equal to 0 to n minus 1. So, the number of complex additions that are needed is n minus 1, whereas the number of multiplications, that is complex multiplication, needed as n into n. Okay, n complex multiplications and n minus 1 complex additions. For each value of k, the direct computation of x of k involves n complex multiplications and n minus 1 complex additions. To compute all n values of DFT, n square complex multiplications and n into n minus 1 complex additions are needed. Okay, for each value of k, how many we need? We need n multiplications and n minus 1 additions. For that, for n point sequence, how many do I need for computing? It will be n into n, that is n square complex multiplications, and number of complex additions will be n into n minus 1. That is, if you see here, for each value of k, I need n complex multiplications. Okay, and for each value of k, how many additions do I need? I need n minus 1 complex additions. This is for each value of k. For n, this will be n into n, that is n square, and this will be n into n minus 1. That is, I need, for the total calculation of DFT, I need n square complex multiplications and n into n minus 1 complex additions. As you see, as the value of n grows, the multiplication sequence is getting bigger and bigger, and also the addition is becoming bigger and bigger. That means the computation time is directly proportional to the value of n. So, as your DFT for complex value is being calculated, for a bigger value is calculated, the time consumed also will grow up proportionately, directly proportional. So, this in effect is one of the main what I call disadvantages of a DFT. Now, let us look at some ways and means where I can reduce the number of additions which are n into n minus 1 additions, or which are complex multiplications which are n square. Now, we have to reduce this. So, how do I reduce this? So, for that we have to calculate some algorithms, try to identify a sequence, try to identify some properties of your DFT which help us in calculation of FFT. What all the calculations which we are doing for DFT is also equally applicable to IDFT also. So, inverse discrete Fourier transform also does involve so many number of complex multiplications and complex additions. Now, let us look at some two properties of the phase factor Wn. What are the properties? First one is called the symmetry property, the other one is called as a periodicity property. Let us see first the symmetry property. Symmetry property says Wn to the power of k plus n by 2 is in fact is equal to minus Wn k. This is the property of symmetry. Then periodicity property, Wn k plus n is equal to Wn k. So, these two are the properties of the phase factor Wn. Let us start looking at the fast Fourier transforms. The first one is called as a radix 2 FFT. So, what is radix 2 FFT? This is an efficient algorithm for the DFT by adopting a divide and conquer approach. This approach depends upon the decomposition of n-point DFT into successfully smaller DFTs. That means, what is actually a fast Fourier transform? Fast Fourier transform is nothing but an algorithm. So, what is the approach or the main idea behind this type of algorithms is called as a divide and conquer approach. So, what does this mean? This means if n is becoming more and more, we have to successfully divide n into smaller number of l's, and all the smaller number of l's then are put together to find out the DFT of a bigger sequence. So, this is called as a fast Fourier transform. In fact, we are doing DFT only, but we are using an algorithm. That algorithm actually makes a DFT into a FFT. So, what does this approach depends upon? The approach depends upon the decomposition of n-point DFT into successfully smaller size DFTs. Let us look at some theory here. If n is factored as n is equal to R1, R2, R3 to RL, where R1 is equal to R2 is equal to up to RL is R, then n is equal to R to the power of L. Then the DFT will be of size, of course, R. then R is called as a radix of the FFT algorithm. Then R is called the radix of the FFT algorithm. So what are we doing? In fact, decomposition of n. So n can be written in terms of R1, R2, R3, R4, R5 up to let us say RL. What is the value of n? If R1 is equal to R2 is equal to R3 is equal to RL, then all this, if I put this all of them equal to RL, then n is nothing but equal to R to the power of L. Okay, because that length of the sequence is L. So where R is called the radix of the fast Fourier transform. Then the another one algorithm which we use is called as a decimation in time algorithm. This is similar to a fast Fourier transform algorithm which we have seen, radix algorithm, where we identified a radix for a system. Here we identify how we can do decimation in time. This algorithm is as follows. Okay, so what we do here is assume that x of n represents a sequence of n values, of course. Then n is an integer of power of 2, that is n is equal to 2 to the power of L. The given sequence is decimated into two n by 2 point sequences, which consists of the even number of values of x of n and the odd numbered values of x of n. So here n is an integer power of 2, that is n is equal to 2 to the power of L. So what I do is I break the n into two parts, n by 2 consisting of even and n by 2 consisting of odd number of values of x of n. So in effect, n is broken into two parts, n by 2 even and n by 2 odd. So let us just repeat the equation which you have written earlier. The endpoint DFT of a sequence x of n is defined as x of k, again summation n is equal to 0 to n minus 1, x of n wn nk, 0 k n minus 1. Okay. So what we will do here, as decimation in time says, we have to break the sequence into two parts. One is an even part and the other one is an odd part. So n by 2 sequence will be even and another remaining n by 2 sequence will be odd. So x of k can be written as something where DFT of even is calculated plus DFT of odd is calculated. So what are we doing here? We are splitting x of n into two even and odd numbered values. So x of k can be calculated by knowing x of n which is even plus x of n which is odd. Okay, then we will use some mathematics here. Then generally put n is equal to r for n is equal to 1 and n is equal to r plus 1 for odd values of n. Then x of k can be written in two terms, one is g of k and other one is h of k. Okay, where g of k is scaled, not scaled, whereas h of k is in fact scaled by a factor w and k, where k varies from 0 to 1 up to n by 2 minus 1. Earlier it was n minus 1. Because we have broken the whole sequence n into odd and even, the sequence length now will be limited to n by 2 minus 1. So x of k, as you see here, is written in two terms, g of k plus w n k h of k, where h of k and g of k, the n by 2 points of DFT of the even and odd number series. So g of k I am using for even numbered series and h of k we are using for odd number of series respectively. So in other words, what is it we have done? A sequence which is of n point has been broken effectively into two equal parts. One of them is called as even part, which is of a length n by 2, and the other one is an odd part of length n by 2. Okay. So again, that means I calculate even part and then I calculate the odd part, either simultaneously or separately. Then we sum them up, then we will calculate the x of k. This in effect we are trying to isolate a little the dependence of number of computations on the length of the sequence n by reducing the number of calculations which we are making. Earlier it was n, now it can be n by 2 as is obvious. Okay. Now for the past few sessions we have seen discrete time Fourier transforms, we have seen discrete Fourier series, we have seen a DFT, then we have seen an FFT. Now let us summarize a few important points in your DFT. Let us recollect what all we have studied, and the summary in fact has been added here to help you in just understanding the whole series of the Fourier transforms by having just a glance at these points. I think there are around 30 points for us to just summarize. We will go through them one by one, and I request all of you to remember these points, which will be extremely useful for you in any competitive exam which you are likely to appear. Okay, let's start with the first point. Okay, as you see here, we have moved from a discrete time Fourier transform to a discrete Fourier transform. From discrete Fourier transform, we have identified what is a FFT. So let us understand these points. Okay, and then let us also come to the conclusion why FFT algorithms are considered the best algorithms of the lot studied so far. Okay, let us look at the first first point. Let us look at the first point of the summary. So let us start with the drawback on DTFT is that the frequency domain representation of a discrete time signal obtained using DTFT will be a continuous function of omega. Okay, there is a drawback. So what is it we are doing here? We are trying to represent a discrete time signal, and when I calculate the DTFT of that, I will get a continuous function of omega. So discrete time, I apply DTFT, I will get a continuous frequency spectrum for that. That is one of the major drawbacks of DTFT. Now, because of this drawback, what is it we have looked at next? We have looked at next what is called as the discrete Fourier transform, that is DFT. So what is a DFT? DFT has been basically developed to convert a continuous function of omega to a discrete function of omega. So first you have taken a time, discrete time, then I apply DTFT, I got a continuous omega, and when I apply a DFT to continuous omega spectrum, I will get a discrete spectrum of omega, that is I will get a discrete Fourier transform. So let me read this again for all of you. The DFT has been developed to convert a continuous function of omega to a discrete function of omega. So this is the advantage, or what I call property, of a discrete Fourier transform. Now let us look at the third point. The DFT of a discrete time signal can be obtained by sampling the DTFT of the signal. So what is it you have done? We said that DTFT is basically a continuous spectrum in omega. Now when I want to get a discrete spectrum of omega, the main operation which we have to do on this is called as a sampling. So let us do some sampling. So if I sample a continuous omega spectrum, I will get a discrete spectrum of omega, which the process of this is called as the discrete Fourier transform. That is the third point. This is done conventionally at n equally spaced frequency points in the period of 0 to 2 pi. Omega is lying between 0 to 2 pi. We generally do the DTFT sampling at a rate which is equal to n. Okay, equally spaced frequency intervals. Now the DFT sequence starts at k is equal to 0, corresponding to omega is equal to 0, but does not include k is equal to 1, corresponding to omega is equal to 2 pi. That is one important point which all of you should remember. So what is that? The DFT sequence in fact starts at k is equal to 0, corresponding to omega is equal to 0, but does not include k is equal to n, corresponding to omega is equal to 2 pi. So this is one of the important points of a DFT sequence. Now sixth point says, the DFT is defined along with the number of samples and is called as endpoint DFT. So whenever we talk about DFT, we should mention the number of samples. That samples we are calling it as a capital endpoint, that is endpoint DFT. Okay. Next point, the number of samples n for finite duration sequence x of n of length L should be such that n is greater than or equal to L in order to avoid aliasing of frequency spectrum. So to prevent aliasing, the important point here is the sampling which I am doing at the rate of n must be greater than or equal to L, where L is the length of x of n. So n is equal to L, that's a very good option, but if not, n must always be greater than or equal to L. Practically, n is slightly kept more than L. So there is a number of samples. So you take this number of samples for a DFT. Now the capital X of k is also called as a discrete Fourier spectrum, also known as signal spectrum of the discrete time signal x of n. As you have seen here in the board, we are representing this x of k. This x of k is nothing but the representation of DFT for a x of n. So this is the notation which we are using. So x of k is also called as a signal spectrum or a discrete frequency spectrum. Now if I plot the samples of a magnitude sequence versus k, then it is called as a magnitude spectrum. The plot of samples of magnitude sequence versus k is called as a magnitude spectrum. Similarly, the plot of samples of phase sequence versus k is called as the phase spectrum. Okay, so can have a magnitude spectrum. When I plot the magnitude sequence versus k, it's called as a magnitude spectrum. Similarly, if I plot the phase versus k, it is called as the phase spectrum. Okay. Similarly, the DFT sequence x of k is periodic with a periodicity of n samples. This is a very important point. The DFT sequence x of k is periodic with n samples. What is the periodicity? The periodicity is n samples. Now, the 12th point of the summary, the DFT of a circular convolution of two sequences is equivalent to product of their individual DFTs. So, if I circularly convolve two DFTs, that is nothing but equal to multiplying the individual DFTs. Let us look at the 13th point. What does this point say? The endpoint DFT of a finite duration sequence can be obtained from the Z transform of the sequence by evaluating the Z transforms at n equally spaced points around the circle. So, this point actually gives us the relationship between the Z transforms and the endpoint DFT. So, just we will understand this a little now again. So, what does this point say? The point says the endpoint DFT of a finite duration sequence can be obtained from the Z transform of the sequence by evaluating the Z transform at n equally spaced points around the unit circle. The 14th point says the DFT supports only circular convolution, and the linear convolution using DFT can be calculated only by the method called as circular convolution. So, this is very important point you should remember. Then look at the 15th point. The 15th point actually speaks of FFT. So, what is FFT? FFT is nothing but a method or an algorithm for computing the DFT with a reduced number of calculations. The stress has been always since our beginning of this session that we want the number of computations to be reduced, to be optimized. So, when I use an algorithm like an FFT algorithm, in effect we are trying to reduce the complexity of a DFT. So, that is what we are talking here. So, when I say complexity means what? I am reducing the number of calculations. So, the FFT is a method or algorithm for computing the DFT with a reduced number of calculations. Okay. Let us be a little specific here. Let us look at the 16th point. So, when you look at an endpoint DFT by radix R FFT, the endpoint DFT we are reducing by a radix R method of FFT, then the number of stages of computations will be m, where m is nothing but log n to the base r. As you see here, the direct representation earlier to n is now changed to the logarithmic scale. So, that is given by number of computations nothing but log n to the base r, where r happens to be the radix of the FFT. If it is radix 2, it will be log n to the base 2. Okay. Now, in direct computations, what is it I am doing? In a direct computation endpoint, the total number of complex additions are n into n minus 1 as we have seen earlier, and total number of complex multiplications are n into n, that is n square. So, this is about a direct computation. When I use an FFT, how does this reduce? So, this is in fact getting reduced when I use a FFT. So, let us get a little bit specific here. So, 18th point, let us look at that. So, 18th point says in computation of endpoint DFT via radix 2 FFT, the total number of complex additions are n log n to the base 2, and the total number of complex multiplications are n by 2 log n to the base 2. So, see what I am doing, the complex additions which are n into n minus 1 now are reduced to just n log n to the base 2, and complex multiplications n into n, now it is reduced to n by 2 into log n to the base 2. So, see the amount of complexities being reduced. That means the number of complex additions which I am making and the number of complex additions multiplications which I am making are reduced as follows. The complex additions are reduced from n into n minus 1 to n log n to the base 2, and the number of complex multiplications are reduced from n into n square to n by 2 into log n to the base 2. So, this is a tremendous improvement, or the speed of operation of your computation has increased by this much. Okay, that is your 18th point. Let us come to 19th point. What does the 19th point say? The complex valued phase factor or twiddle factor Wn is defined as Wn is equal to e to the power of minus j 2 pi by n. This we have defined already. It is also called as a phase factor, it is also called as a twiddle factor, and is represented by the letter capital N, capital W, and is represented by the letter capital W. So, we are representing the twiddle factor as Wn. How much is that equal to e to the power of minus j 2 pi by n. So, what does this term W represents in a phase factor? The term W in a phase factor represents a complex number 1 with a phase angle of minus 2 pi. So, what does term is important? Term W in phase factor is very important, and it represents a complex number 1 with a phase angle of minus 2 pi. Okay, let us look at the 21st point of the summary. So, what does this point say? The multiplication of the phase value minus 2 pi of W by K can be represented as W to the power of K. So, what is this? I am multiplying the phase value minus 2 pi of W by a factor called as K, then it will be equal to or can be represented in terms of W to the power of K, where W is the phase factor or Wn or rather is called as a phase factor or a twiddle factor. Similarly, this 22nd point says the division of the phase value of minus 2 pi of W by n can be represented as Wn. Okay. That is division. In DIT, that is in decimation in time, the time domain sequence is decimated, whereas in DIF, that is decimation in frequency, the frequency domain sequence is decimated. So, DIT, it will be decimation in time, DIF, it will be decimation in frequency, very easy to remember. Let us look at the 24th point. What does this 24th point say? So, 24th point of the summary says, in radix 2 FFT algorithm, the n-point DFT can be realized from two numbers of n by 2 point DFTs. The n by 2 DFT can be realized from two numbers of n by 4 points and of DFT and so on. Let us understand the sequence here. So, what does this point say? In radix 2 FFT algorithm, the n-point DFT can be realized from two numbers of n by 2 point DFTs, and n by 2 can be realized from two numbers of n by 4 points, and n by 4 can be realized from 2 points of n by 8. That means, let us just put this on the board. So, what do we do here is, this n is broken into two numbers. This is n by 2 here and n by 2 here. And again this n by 2 can again be represented by two terms. What are they? N by 4 and n by 4. Similarly, the n by 4 again can be represented by 2 points, that is n by 8 and n by 8. Like this I can do it so on. So, this is one point which you all should understand, why FFT is effective. Okay. So, in radix 2 FFT algorithm, the n point DFT can be realized from two numbers of n by 2 point DFTs. The n by 2 point DFT can be realized from two numbers of n by 4 points of DFT and so on. So, that is the 24th point. Now, let us look at the 25th point. In radix 2 FFT, n by 2 butterflies per stage are required to represent the computational process. So, in radix 2 FFT, what is it we are doing? We are doing n by 2 butterflies per stage are required to represent the computational process. So, everything is broken. So, we call this as a butterflies. So, these for every sequence we need n by 2 per stage to represent the computational process. Let us look at the 26th point. Let us look at two forms. One is a radix 2 DIT FFT and radix 2 DFT FFT. So, in radix 2 DIT FFT, the input should be in bit reversed order and the output will be in normal order. This is a very important point in 26. So, let me repeat this again so that we can understand a little better. In a radix 2 DIT, that is decimation in time fast Fourier transform, the input should be in bit reversed order, whereas the output will be in the normal order. So, this is in the case of a radix 2 DIT. Now, the next point is the case of a radix 2 DIF FFT, the input should be in normal order, whereas the output is in bit reverse order. So, thus we have to understand this 26th and 27th points. One talks about radix 2 DIT, where we want the input to be in the reverse order, bit reversed order, and the output is the normal, whereas the 27th point says radix 2 DIF FFT, the input should be in normal order and the output should be in a bit reverse order. So, this sequence you should remember correctly. Then 28th point, in butterfly computation of DIT, the complex multiplication takes place before the add subtract operation. So, this is again important point. What is that? In butterfly computation of DIT, the complex multiplication takes place first, later comes the addition or subtraction operation altogether. 29th point. In butterfly computation of DIF, the complex multiplication takes place after the add subtract operation. Okay, so earlier point we said that multiplication is done first, but here now in butterfly computation of DIF, the complex multiplications takes place after the add subtract operation. Finally, the 30th point. So, what does this point say? In FFT, the phase factor for computing inverse DFT will be conjugate of phase factors for computing the DFT. That means, the phase factor to calculate the inverse DFT will be the conjugate of phase factors for computing the DFT. Now, all these 30 points are very important, where we have put a summary of what we have learned so far. So, as you have seen in this summary, we have avoided involving any formulas. Whereas we have gone beyond the formula, we have found out what is the time complexity of calculating a DFT, what is the time complexity in calculating a radix 2 FFT or a radix R FFT signals like that. Then we also found out what are the different rules which are applicable for DIT, what are the different rules applicable for DIF techniques. So, all this we have seen. So, these 30 points seems to be a consolidation of what we have studied in the past so many sessions. So, this will actually help you in understanding the DFT better. So, while reading these 30 points, my advice to all of you is, if you get any difficulty or any point which you are not able to understand, go back to the sessions, try to understand them, refer to some books if possible, then you can clear the doubt. But make sure the 30 points go into your mind very deep and they are embedded in your mind, so that you can use these techniques wherever asked and you can apply them wherever needed.